The first one here is investigating the range of radiation. So what you might have is some kind of detector, and I'll just say a wee bit more about detector. And that detector is generally connected to some kind of meter which counts, a count rate meter. So sometimes they call it a rate meter. And this is a detector. Now the first thing you have to measure is background radiation. And to measure background radiation, you have to count for say 5 minutes. Just switch your detector on and allow it to count, and you'll see the rate meter going up. And then do a calculation and divide the radiation detected by the number of minutes, and that will give you your count rate per minute. I'll give you a count rate per minute. Now that shouldn't be too high. It might be something like 12 counts per minute or something like that. It shouldn't be too high. Then, if you then wanted to look at the range of your radiation for any particular source, you would take your source, you would place it in front of your detector, say fairly close, and then you would move it back. And you would get to a point where, say there, where your radiation has just gone down to the background. So whenever it reaches background radiation again, that is the range or distance. I suppose I should really have that right up at the counter or the detector. And you're moving your source back until you get to the furthest distance where you're just detecting the background count. And that is the range of your radiation. And record your results. So you could do that for different sources. That's getting you your range of radiation. A couple of wee questions at the bottom here. Name 3 possible sources of background radiation you recorded. Well, it's in a classroom, so it could be coming from rocks and soil underneath. It could be coming from your bones. It could be coming from any food present. It could be some kind of cosmic radiation which is getting in, and so on. Which type of radiation had the shortest range? Now the shortest range is the alpha radiation has got the shortest range. Which type of radiation would be most dangerous 10 meters away from you? Why? And the answer is that it's gamma, and it's got a very long range. Now the problem is, of course, with all these radiations, we can't see them and we can't feel them, and it would only be long term that maybe you might have effects, some kind of illness like cancer or something from too much radiation, but you wouldn't know about it at the time. A second experiment, and this is penetrating power. This experiment came up last year on the GCSE, that was 2009. And again, first thing you do is measure the background radiation reading using a radiation detector. Now, number 2, you would set your source at a certain distance from your detector and keep it there. And again, your detector's connected to your rate meter again. And then in between your source and your detector, you would start putting different thicknesses of, first of all, paper, and then aluminium, then thicker aluminium, and then lead. And build that up until, again, you're right back down to background count rate. And when you have done that, you have discovered the penetrating power of your particular type of radiation. So if it was alpha radiation, then you would expect that the thin piece of paper would be able to stop that, and you would be back down to your background count rate here on your detector or on your rate meter very, very quickly. So if you did that, which type of radiation was least penetrating? And the answer is alpha. Which type of radiation would be most dangerous outside your body, and why? And the type of radiation that would be most dangerous outside your body is gamma. And the reason is because it's very penetrating. Now, the next question said, which would be most dangerous inside your body? And this is a question, that type of question, people get wrong all the time. Inside your body is different. You know that alpha is absorbed very quickly by paper or by your skin. So it isn't going to get very far. It will be absorbed by your skin if it's outside your body, so it's least dangerous. Although that could give you a radiation dose in your skin. But if it's inside your body, it doesn't have to go very far before it's absorbed. And that means internally, you're going to be getting lots of radiation dose from an alpha source. So in other words, if you swallowed it, which isn't very likely, but hopefully you wouldn't do that. So the answer there is alpha, and that's because it has the shortest range and very easily absorbed. And that's very, very dangerous for you. Right, the penetration power of the 3 types of radiation. And so this just shows what the 3 types of radiation. Alpha is stopped very easily by skin or paper. I'm not sure what mica is. It must be very, very thin paper. So it's stopped, and the reason is because it's so heavy, but also because it's very, very ionizing, and we'll talk about that in a minute. Beta, which are electrons, can pass through thin mica. It can pass through skin or paper. But once it gets to a few millimeters of aluminium, then it is stopped. Gamma, however, can pass through all of them. It gets to lead. It does reduce, the lead reduces its energy, but may not stop it completely. And so your detector will be able to take gamma radiation right through all those different things there. And that's what makes gamma so dangerous to us outside our bodies. Okay, the effect by a magnetic field. Again, what you can do is, and I think I won't show this to you, I'll just go on to the next slide to see. What all you have to do there is set a detector over here somewhere and look at the radiation passing through. So if this is a magnetic field here, it could be a magnetic or electric field. And what happens is that beta radiation has a small is charged and has a small mass, so it will be strongly deflected. Okay, so anything that's charged will be affected by a magnetic or electric field, and beta is also. Gamma radiation has no charge and no mass, and it's not deflected at all. So if you had a detector sitting here, your detector would still be picking up your gamma radiation. If your detector was sitting here and you were trying to pick up alpha, you wouldn't have much luck because it was actually deflected down here. And alpha radiation has a +2 charge but a mass of 4, so it is only weakly deflected. So the heaviest particle, alpha, is deflected by a small amount. The lightest particle, beta, is deflected by a large amount. They're both charged, so they're both deflected, but gamma has no mass or charge and isn't deflected at all. So this is a summary of the properties of radiation. Penetrating power,